In this video, we're going to talk about basic programming concepts. The purpose of this video is to give you a background in these concepts so that when we discuss these during practices, these terms are more familiar. Also, when it comes time to present this material to the judges, you'll be able to provide a better explanation of what is happening in our code. Note in the description that this video contains chapter marks, so when you want to review this video, you can jump directly to the part you want to review. First, we'll start with variables. The power of programming comes from telling a computer to do the same thing over and over again. Computers are very good at this. The first thing we are going to tell a computer to do over and over again is to use a value. This is called a variable. Every programming language everywhere uses variables. You can think of a variable as a box that stores a value. Here, we're going to say x equals 1. That is, a box named x has a value of 1 inside of it. There are two main ways that variables are used in programming: tracking a value that changes and tracking a value that doesn't change. Let's look at a simple example. Let's say you're writing a scoreboard program. You'll use a variable called score, which will change each time the player scores a goal. We'll start by setting the score to 0. Now, we're going to write a simple line of code to increment our score. That is, when a player makes a goal, the score goes up by 1. And that becomes the new score. This can be read, score equals score plus 1. I'm going to add a 1-second wait so that we can watch our progress as it goes. Otherwise, it would be over too quickly. I'm going to add a display window so we can watch our variable's value change. Now, I'm going to right-click and duplicate these lines 5 times so that our score simply goes up to 5. And then we'll celebrate with a squeaky toy sound. So let's run our program and see what happens. As expected, our score simply increases to 5. And a squeaky toy. Okay, wait. You didn't want hockey goals? You wanted field goals? Fine. All of these 1s need to be changed to 3s. But we can make this simpler on ourselves by introducing a new variable called points per goal. This type of variable is one that won't change, which is known as a constant. We set this value once so that we don't have to keep setting it each time we want to use it. The advantage here is that if we change it, we only need to change it one time, and that changes it throughout our entire program. Some programming languages set constants and variables differently, but in Scratch, they're all the same. So let's go back to our example. Now our line reads score equals score plus points per goal. We are going to increment our score by the number of points that each goal is worth. Wait, what? You want basketball field goals? Yes, I know that's technically what they're called, but who actually calls them that? Fine, whatever, basketball. We can simply reuse our program with a different value for points per goal. Variables are super useful this way. As a brief side note, let's look back at our line score equals score plus points per goal. The name of the basic mathematical function that changes a value is called an operator. There are 4 basic arithmetic operators: addition, subtraction, multiplication, and division. There are other types of operators, but we'll start here. So now that we have our values, it's time to make decisions based on those values. The main way that a computer makes decisions introduces our next common programming concept called if-then and if-then-else. Let's say we're going to play our game up to 5 goals, which is 10 points now that we're playing basketball. If the game is over, we're going to celebrate with our squeaky toy sound. So we increment our score by points per goal, and then we check. Is score equal to 10? No? So no squeaky sound. This introduces another critical programming concept, the Boolean. Boolean is a mathematical term that means true or false. A Boolean value can only ever have one of those two values, true or false, although sometimes you'll see these represented by 1 and 0. A Boolean value gets to the true nature at the core of computing. A binary value. Binary simply means 0 or 1. Everything that computers do is simply a fancy representation of lots and lots of zeros and ones. In Scratch, Booleans are represented by this hexagonal shape. So let's go back to our scoreboard. We can make this a little more useful if we add an alternative to our if-then. Let's instead make this an if-then-else. Now we're saying if score equals 10, then squeak our squeaky toy, otherwise, or else, increment our score. Now when we run our program, we see that we don't get our squeaky toy sound, but our score did go up by 2. So, if we duplicate this 5 times, our score reaches 10, and we finally get our squeaky toy sound. And what if we want to count up to 20? It works, but now our program looks ridiculous. So let's clean this up with a loop. A loop is another crucial programming concept. A loop tells a program to redo something over and over again. There's that telling a computer to do something over and over again. Are you seeing a pattern here? Scratch uses 3 main flavors of loops. Loop forever, loop a certain number of times, and loop until something happens. Loop forever is pretty easy. Just keep looping, typically until the user stops the program. Loop a certain number of times is also pretty easy to understand. Just loop until you reach that number. Loop until, though, brings in another Boolean. In other words, loop until this thing is true. If you think about it, all 3 of these are just variations of loop until. To make a loop run forever, simply place a Boolean there that will never be true, like 0 equals 1. No matter how many times you loop through this loop, 0 will never equal 1. Believe me, I've tried. To make a loop run a certain number of times, we would simply make a variable counter equal to 0. Then we place an incrementer line inside the loop, and finally we set loop to loop until counter equals your desired number of loops. Let's say 5. Now this creates a specific kind of loop, the feedback loop. What happens here is that the loop makes a small change to the variables and then feeds that value back into the loop to see if the appropriate conditions have been met. In this case, does counter equal 5? No? Then make one more pass through the loop, making another small modification, and feed the value back through the loop again. Rinse and repeat until the condition is met and the feedback loop is complete. So let's look at our scoreboard again. Instead of all these if-thens, we can replace all of this with a simple loop. Let's set loop until to score equals 10 and place this if-then-else inside the loop. Now when you run the program, you get the exact same result, except with much more efficient code. You really begin to see this when we only count to 10, but what about 10,000? If we had to duplicate those lines 10,000 times like our last program, it would take quite a while. Now we just change one variable. So we have our score counter, but let's say we want to include a countdown clock. We're going to take a brief detour for a few minutes here and give our score counter a mechanical representation. We're going to make our motors show the user what the clock and score are by moving the motors 10 degrees for every increment, whether it's a second on the clock or a point from a goal. Imagine an analog clock with a minute hand but no hour hand. Let's use motor C for our clock. The first thing we need to do is add a new variable called degrees per tick, which we'll set to 10. We want the motor to move 10 degrees for every tick. Again, whether it's a second on the clock or a point on the scoreboard. Let's say we want our game to last 15 seconds. So we're going to set our clock to count down starting at 15. Since we're using 10 degrees per tick, we start by setting our clock's position, motor C, to 15 seconds, or ticks, by 10 degrees per tick equals 150 degrees. Now, we're going to do something a little complicated, so hang with me for a minute. I'll explain why we're doing this later, but for now, we're not going to use a standard variable to keep track of our clock. Instead, we're going to use the motor's position to tell us what the current time is. In order to figure out what the current time is from the position of the motor, we need to do a little math. First, we need to find out what the current position is, which we will temporarily set in a variable called motor C position. Then, since we set our degrees per tick variable to 10, we need to divide this value by degrees per tick. One thing to keep in mind about programming with the LEGO Robotics motors is that they are not finely tuned engineering marvels. They are good enough to get the job done, but they are not super precise. So, we're going to allow for them to be off by a little bit by simply rounding to the nearest 10 here and calling it good. They may not hit the exact degree precisely, but they'll get within 10 degrees. Let's review our math. If we told motor C to start at 150 degrees, and then we divided that by 10 degrees per tick, we get 15, which is exactly the number of seconds we want our countdown clock to count down from. So what do we need to do with this value? We need to subtract by 1 for every pass through our feedback loop. Counting is a common programming function, and programs typically call this incrementing. However, when you're counting down instead of up, it's called decrementing. Finally, we need to figure out how many degrees to tell our motor to move to by multiplying this new value by degrees per tick, taking our new value of 14 seconds to 140 degrees, and then tell the motor to move there. We'll put our new command in the feedback loop, but now we need to determine exactly what the condition is that our feedback loop is aiming for. We know that our game is done when the countdown timer reaches 0, but how do we represent that using our motor? When the motor moves past 0 degrees, it will flip back over to 359 degrees. So if our motor value is greater than, say, 345 degrees, again, accounting for these motors not being the most precise things ever, then we'll know we got there. Finally, this is a countdown timer, so we'll let our players know the game is over with a buzzer. Let's try it. I'll put a graphical representation of the motor up here so you can keep track of its position more easily. As you can see, it works pretty well. For our next trick, we're going to add our scoreboard counter. We're going to duplicate this code, except using motor A to keep track of our score. Then we're going to need a variable called motor A position and change all of these variables. If we're going to use motor A for this, we'll first need to set motor A to 0 when we start. Since we want motor A to increase every time a basket is made, we need to change this math here to say +2 instead of -1. Then we're going to make a loop that says our player scores one basket exactly every 1.6 seconds for the next, well, forever. He's a scoring machine. And every time he scores, he gets a whiz sound. We'll set the loop as forever right now, but we'll stop it in another way in a second. So, we have our lines of code over here, but how do we call it? That brings us to our next main concept, messages. Messages come in two flavors, broadcast and wait and broadcast without wait. So we'll use a message. If we put a broadcast and wait in our main program here, the broadcast and wait is going to send a message to this portion of the code over there saying, hey, go ahead and run your lines of code now, and I will wait for you to complete them. Then, when that code completes, the program starts running again at the line it left off from. The true power of a message block comes, though, when you use broadcast without wait, because then your message portion of the code will start running, and the main portion of the code will keep running at the same time. As a matter of fact, we're going to call two messages using broadcast without wait, one for player 1 and one for the clock. So look at what's happening. Our countdown timer keeps counting down while our score is counting up. Using broadcast without wait allows us to do a very simple instance of a concept called multi-threading. Multi-threading is where a processor is able to run two different bits of code at the same time. This is a very important concept for modern computing because this way your processor doesn't get stuck waiting for one program to finish before another program can begin. You can have multiple threads running at the same time. Now, just for kicks, we're going to add in player 2. This player will shoot threes, but he'll only be able to shoot at a rate of once every 2.1 seconds. So now we have 3 threads running, 2 which appear to be running forever. How do we tell them to stop? One quick way is to tell our clock message block to end the program once it reaches the end of its loop. We'll put a stop and end program here, and that will stop all the loops. I guess forever didn't mean forever after all. Maybe forever should be labeled forever or until something else stops this, whichever comes first. Now we'll test our program and see what happens. The players each get their sounds every time they score. The scoreboard counter goes up, the timer counter goes down, and there's a buzzer marking the end of the match. Nice! It looks like player 2 pulled it out. We have a nice little program here, but there's one thing that could make it better. If you look at our message blocks, we're doing the same thing over and over again. Every time you find yourself doing the same thing over and over again when you're programming, you should ask yourself, is there a better way to do this? And in this case, there is. This brings us to our last major concept we'll cover in this video, MyBlocks. MyBlocks are similar-ish to messages with a couple of key differences. First of all, MyBlocks are Scratch's version of subroutines. A subroutine is a small portion of code that your program is going to run over and over again because what are computers very good at? Running things over and over. You get the idea. Subroutines are a very common programming concept that all programming languages use. As an example, look at the code that scores player 2 and the code that scores player 1. It's the same. Wait a minute, you say. One scores 2 points and one scores 3 points. They're not the same. This is where a key programming concept called parameters comes into play. Parameters are a special kind of variable that are passed into a MyBlock and are only used for as long as that MyBlock is active. Then, the parameter ceases to exist until the next time the MyBlock is used. And this is one major difference between MyBlocks and messages. Messages cannot send parameters. So how can we use a MyBlock in our case? We'll make a new MyBlock called changer, and we'll give it one parameter called ticks per change. This will take the number of ticks that this MyBlock needs to change the motor position every time it's called, and it will calculate the rest. To start with, we'll relocate all the motor position math, the go-to position line, and start sound line to our new subroutine changer. But looking at this line, it specifically calls motor A, and it calls it for 2 ticks per change. So how do we change that? Remember, if there's a decision for the computer to make, we'll use an if-then-else. Let's make new variables simply called motor and a generic motor position and say if ticks per change is 2, then motor equals A, else motor equals E. Now we drop motor and ticks per change variables into our motor position math and go to position line, and we're looking pretty good. But what about the sound? I hear you asking. Anytime there's an oval in Scratch, we can simply replace it with a value using a variable. That's how we got the motor to work. So we'll add a new sound variable to our if-then-else and say for 2, sound is whiz1. Otherwise, use whiz2. The last thing we need to do is call our MyBlock from our message blocks, and we're set. Before we test our program, let's talk briefly about the words subroutine and function. Sometimes you'll hear a subroutine referred to as a function, even though a function and a subroutine are technically different. A subroutine is a series of code that does a thing, and that's it. It's called a subroutine because it is subordinate to the main routine. The main routine stops when the subroutine is called and waits for the subroutine to complete. At that point, the main routine picks up where it left off. A function behaves the same way, except when it is done, it returns a value. You can think of a function as the same as a mathematical function. If you have x plus y equals z as your mathematical function, and then you were to make x equal to 1 and y equal to 2, your mathematical function would return a value of 3. Now, even though I just explained that a portion of code needs to return something in order to technically be a function, the words function and subroutine are basically used interchangeably by programmers at this point. Someone will say function to describe some code, and someone else will say subroutine, and they take it to mean the same thing, so don't get too hung up on it. As a programming language, Scratch does not have the capability for a MyBlock to return a value, so all MyBlocks are technically subroutines, but occasionally people may still call them functions. And it's not that Scratch does not have functions at all. Scratch does have functions. They're just predefined and not something that the user can create. Every time you use one of the green ovals, you're calling a function. Remember my mathematical function example, 1 plus 2 equals 3? That's exactly what this function does. You send 1 and 2 as parameters, and this oval function returns a value of 3. One final thing to note about subroutines. One limitation of Scratch is that you cannot pass a variable into a subroutine as a parameter. You can only pass the variable's value. This goes back to our decision to use the motor locations to track our score. The subroutines cannot be told which variable to retrieve a value from, but they can be told to retrieve the position of a motor. In this way, we use the motor's position as a kind of pseudo-variable or a fake variable to overcome this limitation of Scratch. Having said all of that, let's test our program. We run it. And sure enough, we get the same response as before. And player 2 still won. He's on a hot streak. This code looks pretty good, but there's still one other change we can make. We basically use the same code again in the clock message block. Okay, now hold on. There you're subtracting a value, not adding it, I can hear you say. But is there a way we can add to subtract? How about if we add a negative number? We place -1 here, and that will make our value go down. So technically we are incrementing here, but incrementing by -1. Now we need to account for our motor. Right now, We're saying if the ticks per change is 2, then set motor to A. But in all other cases, set motor to E. -1 would set the motor to E, but we need it to be set to C. Some other programming languages would solve this using a command called else if, or maybe a command called select case. But Scratch tries to keep it simple and doesn't have either of these commands. So we'll just nest one if then else inside another if then else. Now if ticks per change is greater than 0, do these things, otherwise set motor to C. Yeah, so what about the sound? The clock doesn't even make a sound for each change. Yes, that's true. But if we call a sound name that does not exist, such as X, Scratch will just ignore that line and not make a sound either. Now let's run our program again to make sure everything still works. Yep, it was a close game, but player 2 pulled it out again, and all of our sounds fell in the right spots. Our program is looking really good now, but there's one more change we can make and one more minor concept we can introduce. Let's clean up our code by placing all of our initialization values into their own subroutine. We'll create a MyBlock called initSettings and clean all of this stuff that sets up our program before we begin. That way, if you're troubleshooting your code later, you don't have to wade through 10 lines of setup stuff before getting to your actual program. Now, initSettings won't have any parameters itself. It's just something we'll run. While we're at it, we're also going to follow good programming practices and standardize our values into variables. We'll add a variable for points per 2-point goal and points per 3-point goal. Then we'll make variables for motors and sounds. Finally, we'll call initSettings at the beginning of our program, give it a 2-second delay to make sure the players are ready, and whistle them to start. Here are 2 quick points I want to make about creating an initSettings subroutine. First, as we mentioned before, this is a programming best practice, since all of the values that might be changed about your program, such as the motor assignments and the point assignments, are all gathered in one place. If you need to make a change, you don't have to play hide and seek with your values and hunt all over the place, trying to find all the nooks and crannies in your code that the changes need to be made. Secondly, though, this introduces another programming concept, the global. In most programming languages, typically a variable is only used in one subroutine or function and then passed from one to the other as a parameter. However, if a variable is used everywhere in the program, that is called a global. You can see that these variables are called in the initSettings subroutine, but then they are used in all these different places. Most programming languages need to establish globals in a special way, but since Scratch is a beginner's programming language, Scratch simply assigns every variable as a global. It just makes things easier. Now we have a very solid program here. There's one last thing we could do, but admittedly, this is more of a style choice, and there are arguments both ways. We could nest all of this math into a single line like this. Some people like to do this on the principle that fewer lines of code is always the more elegant solution. But others argue that to break a function like this out into several lines makes it easier to read and troubleshoot later. That's honestly a judgment call. Let's run it one last time. Player 2 still won. That guy's on fire. Okay, let's review. We can use an initSettings subroutine to call our initial variables. Some of these are constants, and some of these are used as globals, even though all variables in Scratch are technically globals. We also use init settings to position the motors to their starting positions. Once out of init settings, a whistle blows and our main routine multi-threads 3 message blocks, running them all simultaneously. The clock message block uses a Boolean to determine when its feedback loop is complete. Inside the feedback loop, the clock motor's position is incremented by -1, or decremented if you prefer, using our changer subroutine. The player 1 and player 2 message blocks increment their players' scores every few seconds. All 3 message blocks call the changer subroutine. The changer subroutine receives the ticks per change value as a parameter. It uses a nested if-then-else to determine which motors to change, as well as which sound and tick counts to use. Then it retrieves the motor's current position and does the appropriate math to determine the motor's new position before telling the motor to move to that new position. And at the end of it all, we get a buzzer. There's one final thing I want to cover in this video, and that is some other terms and phrases you should be familiar with when working with programming. To start with, a program is made up of all your lines of code, your functions, and your subroutines that make the computer do the thing. A program can also be referred to as code. A script is a very simple program that sometimes may come as some assembly required. That is, the user needs to do something in order to make it complete. Subroutines and functions can sometimes come packaged together in a library, and users can often find libraries written by others that are packaged together to be released to the end user. Applications and libraries need to be thoroughly tested before they can be released. Let's take a closer look at the program itself. The program is written in a specific language, such as Scratch or Python. The programmer writes the program in an editor. For example, Scratch for LEGO Robotics is written in the Spike app editor, while Python may be written in Visual Studio Code as an editor. Before the program can run, it needs to be compiled, which is to say converted into machine language, but that is usually done automatically by the editor these days. Machine language is the final language that the computer actually runs, and it is written in hexadecimal, or base 16, where the numbers count from 0 to F. And last but not least, the LEGO Spike Prime Hub is an ARM Cortex M4 32-bit microcontroller with 256 kilobytes of RAM and 1 megabyte of flash storage for programs. It uses Bluetooth 4.2 for wireless control, has a USB 2.0 port for charging, and has a 21 milliamp hour lithium-ion battery. It runs on custom LEGO firmware, which is based on MicroPython. And with that, you're done. You made it. 31 minutes of programming awesomeness. Feel free to re-watch this as many times as necessary, or skip to the parts you need to review. Good luck, and we'll see you in the next video.